So this is published now. It's inhibitory co-transmission from midbrain dopamine neurons relies on presynaptic GABA uptake.
It's more midbrain dopamine. Okay,
It's
nice.
more midbrain dopamine. So this is a paper. It's been published in Cell Reports by the lab of Nicholas Tritch and Riccardo Milani. I don't know Riccardo, I don't know the first author, but Nick Tritch, great guy. In Cell Reports. And they demonstrate, so dopamine neurons, you would say, okay, they release dopamine, right?
Yes.
Wrong. So dopamine neurons can actually also release GABA. And dopamine is it's a neuromodulator. It can be excitatory or inhibitory. GABA is generally only inhibitory. But it acts much faster. Striatum is full of it. Like the entire striatum is full of GABA. Because all the neurons in the striatum are GABAergic, except for the cholinergic neurons, which is what makes the cholinergic so cool. And so the striatum has a lot of GABA going around, and a lot of local neurons, projecting in very small distances that release GABA. And it turned out, and I think this is actually, it's not entirely new, we knew this already, but it turns out that the midbrain dopamine neurons can also release GABA. And here Nicholas Tritch and Riccardo Milani demonstrate how that can happen. So the substantia nigra dopamine neurons release GABA through an unconventional mechanism. So it depends on GAT1. I don't actually know what GAT does. So the bottom line is these dopamine neurons do not produce GABA themselves because they do not have the machinery to produce GABA.
Yeah, is GAT some precursor for the GABA? Or
LDH1H might be. But you can abolish this GABA co-release by deleting VMAT2, which...
What's that?
That was my question too. VMAT2 is the vesicular monoamine transporter. So basically what this does is you have a dopamine axon and it's in the striatum, right? And the striatum is full of GABA. The dopamine axon says, tasty GABA. It takes it up, it transports it, and releases it. So these dopamine axons just take up GABA from the extracellular environment and release it. So GABA synthesis requires aldehyde dehydrogenase 1A1, but that's not required. That's not included in these dopamine neurons. Here they demonstrate that the dopamine axons obtain GABA exclusively through presynaptic uptake using a membrane GABA transporter. GAT1. So GAT1 is the membrane GABA transporter. And then it's packaged for vesicular release using the vesicular monoamine transporter VMAT2. So there's two transporters that are required. So one to take it up and then one to release it again.
Okay. But they say that this GAT1 is a transporter because I secretly Googled it and it's here on Google on the gene cards. It says that it's also an enzyme, so it can aid in the production of GABA from L-glutamatic acids. I don't know. So now I'm not completely sure what this GAT1 does. I'm very confused. But here in this paper they say it helps. So maybe in these neurons it helps with transport, GABA transport.
I guess so, yeah. So that's here, we see the role for GAT1 here.
No, I got your GAT1 wrong, sorry.
And then VMAT2 packages it into vesicles where it can be released.
I thought of something else when you said GAT1. With a D.
No. Not GAT with a D. That's a completely different thing.
Completely, yeah. That's what I looked up. That's like, I know that GAT1 with a D, but.
And they say biology is difficult. It's super straightforward. So yeah, more happy news and more mysteries that have been unraveled in the stratum.
Well, that's very cool. So wait, then let me understand the importance of this paper for now. So there are dopaminergic neurons that have like these long projections, and they cannot actually make any GABA. They're not really GABAergic, but they can like magically release GABA in the striatum because they just take it.
Yep.
So we don't have to call them GABAergic neurons, I guess. They're still
No.
only dopamine neurons. This is very fascinating. Yes.
There is another population of neurons in the substantia nigra, in the same part of your midbrain, that also projects to the striatum that is GABAergic. And they do express VGAT, which is the vesicular GABA aminotransporter, I think. It's been a while. But those do not co-release dopamine. They only release GABA. But they produce it as well. So there's a population that produces GABA and then releases it. And there's a population that produces dopamine and takes up GABA and releases both.
Yeah, this is...
it's horribly complex. I love it.
Yeah.
It's a wonderful system.
But we don't know. So then there's more GABA. Like there's like GABA reuptake. So there's more GABA available in the striatum with these neurons doing this reuptake, right? And re-release. Yeah.
Pretty much.
And they can redistribute it. So, or do they speculate? So now I'm speculating to the function of this wonderful new system that they discovered. Maybe they speculate in their discussion also.
It's a bit of a mystery for me. I didn't read the discussion yet, but one of the issues with this is we noticed that, well, I mentioned the cholinergic neurons, right? They receive very strong GABAergic input from these dopamine axons.
Okay.
So not only do the dopamine neurons, dopamine, it blocks the communication between the cholinergic neurons. They also directly inhibit the cholinergic neurons through this GABA release, which has a very strong effect actually on the cholinergic neurons. We didn't do a comparison with other neural types, but they do seem to be one of the main recipients of this GABA. So it's another way in which the dopamine and acetylcholine systems interact in the striatum.
Wait, would you think that this GABA maybe helps this pause that is very famous in the striatum?
You've been paying attention.
Little bit. Sometimes I pay a little bit of attention of what these crazy striatum people say. I don't even know what's the function of the pause, but I know it's very important.
The striatum people also don't know the function of the pause. If they tell you they know...
This is probably why I don't have this clear.
We're making it up as we go along. Don't tell anyone. From what I can tell, and we've done a little bit of, looking into this. From what we can tell, it does not directly cause the pause.
Okay.
Which seems to be more strongly correlated with local interneurons or cortical afferents. Feng Zhang, I think is his name, in Stephanie Craig's lab, had a manuscript where they demonstrated cortical afferents or like a cessation of cortical input causing the pause, or there was some correlation. Okay. But there may be other reasons. It may just be an intrinsic network property of the cholinergic network. Like they have the ability to pause, and that ability can be triggered through a variety of means. And that is what I personally believe. I think personally that it's just, there are multiple ways to trigger this, and it's the local inhibitory neurons that connect them that are responsible for the pause, because they have a very strong GABAergic inhibition on the chins. If that is true, we'll see.
Wait.
It seems to be almost like a network state. Once the cholinergic neurons become too synchronized, they fire in synchrony, they trigger the inhibitory pathway between them, then they all pause for a little bit.
Okay. That could be. It's like a network
I'm
oscillation.
hypothesizing here. We have no evidence.
Yeah, that's maybe too simple. If there are multiple ways to induce the pause.
It's at least a good way to keep friends in the community, You're not wrong. We're just both right.
Very good.